Hello, this is the section 2.2 lesson. In chapter 2, we're going to start studying the idea of random variables in depth. Random variables are something that we introduced back in chapter 1, and they are extremely important because they form the foundation of everything we're going to do for the rest of the semester. You're going to get very sick of me saying the phrase random variables. In section 2.2, we're going to also introduce what we call the probability mass function. But let's start off by talking about what are random variables. Informally, a random variable is a rule for assigning a real number to each outcome of a random experiment. So we're going to do some sort of random experiment. With each outcome, we associate a real number, and that rule for assigning things is what we call a random variable. So a couple of examples. Suppose we randomly select a fish from a lake. Let the random variable z denote the length of the fish in inches. Okay, so here, an outcome to this to this experiment is a fish. The random variable is the length of the fish. That's a real number. Okay. Another example: a voter is randomly selected and asked if he or she supports a candidate running for office. Let the random variable w equal 1 if the person supports the candidate and 0 otherwise. So here, an outcome to this random experiment is a person. Our random variable is 1 or 0. It takes on one of those two values. So this definition 211 is a little more formal definition of a random variable. It's a little bit abstract, but it says let S be the sample space of a random experiment. A random variable is a function that maps that sample space over to the real numbers. Remember that this symbol here, this kind of bold case or script case R, stands for the real numbers. So random variable is a function that takes the outcomes, maps over the real numbers. The set of possible values of our random variable is called the range of the random variable. Range, same word that you used back in high school algebra when you first introduced functions. Range of a function was the set of possible outputs or possible values. No difference here. Okay. Now, this definition is a bit abstract, so let's make some practical comments about it. Number one, a random variable is a function. Okay. It takes in an outcome from our random experiment and returns a real number. Okay. Number two, a random variable is not a probability. Okay. Random variable is not just another term for a probability. It's a completely different idea, but closely related. Okay. Number three, random variables can be defined in practically any way. Their values do not have to be positive or between 0 and 1 as with probabilities. Okay. Random variable could take on negative values, it could take on decimal values, it could take on numbers greater than 0, values greater than 0, a lot of possible ways. Now, there are some limitations as to how we can define random variables, but we're not going to get into that right now. Okay. Number four is a comment about notation. Random variables are typically named using capital letters such as x, y, and z. And we'll use the random variable x a lot. Values of the random variables are denoted with their respective lowercase letters. Thus, the expression capital X equals little x means that the random variable capital X takes on the value little x. So that expression capital X equals little x looks a little weird the first time you see it. We often think capital letters mean the same things as lowercase letters, but that's not the case here. Capital X is the name of the random variable, or the name of the function. Little x is the value of the function. Okay. Now, in this book, we're going to study two different types of random variables: discrete and continuous. Here in this definition, we define what a discrete random variable means. A random variable is discrete if its range is either finite or countable. Range is finite means that there's just a finite number of values in its range. Countable means that you could line up those values as like the first, the second, the third, so on and so forth. Now, chapter 3, we're going to study continuous random variables. We won't give a formal definition here, other than to say they're kind of like the opposite of discrete random variables, but that's not the formal definition. Okay. Now let's make an observation here about these random variables. The values of a random variable are determined by chance. Think about the fish example. We randomly select a fish from the lake, and therefore its length is random. Okay, we randomly select a voter. Whether that person supports the candidate or not is random. Everything is random. Okay, and so that means there's a lot of probabilities involved here. We want to describe the probabilities of these values. Like with the candidate or the selecting the voter, we might want to know what's the probability that x equals 0 or the probability that x equals 1. Everything's determined by chance. We want to describe those possibilities or those likelihoods with probabilities. Okay, and so to do that, we're going to define this function, call it little f. Little f of little x equals the probability that capital X equals little x. Okay, now that's a rather short equation there, but rather complicated. So we're defining this function little f, and the input to this function is little x. That's going to equal the probability that our random variable capital X equals that value little x. And so this function is what we call the probability mass function, abbreviated PMF. Okay. So this is kind of an informal introduction to the idea of a probability mass function. Let's give a little bit more formal definition of this. So it says let x be a discrete random variable and let r be the range. The probability mass function of x is a function, little f, that's going to take those values of the random variable and map them to the real numbers. And it satisfies the following three properties. Okay, so let's stop right there for a second. So probability mass function is a function, meaning it's going to take in something and spit out something else. In this case, it takes in values of the random variable, which are real numbers, and then it's going to return another real number. Okay. But this is not just another type of random variable. It's a function that satisfies the following three properties. Number one, f of x has to be greater than 0 for all x in the range. So it's saying that this probability mass function can never be negative. Number two, if we add up all the values of this function over all possible values in the range, it should equal 1. Okay. The third property is really a description of how we're going to use this probability mass function. It says that if A is a subset of R, so if A is a collection of values of the random variable, then the probability that x takes on a value in that collection is equal to the sum of the PMF over the values in that set A. Okay. Now let's that definition is a little abstract, and so we're going to illustrate that in an example here. But before we do that, let's go to another definition. This is another term that we saw back in Chapter 1, the distribution. The distribution of a random variable is a description of the probabilities of the values of the variable. And this can be given in three different forms: a table, a graph, or a formula. And we're going to see all three of these different types of descriptions throughout the semester. Alright, so now let's try to illustrate these rather abstract definitions with a little more concrete example. So consider a bag that contains one red and one blue cube. Okay, so very simple example. Suppose we randomly select two cubes with replacement. So we're going to select one cube, put it back, select a second cube. The two cubes we select are called the sample. Okay, the sample space in this case is the set RR, which means we get a red and a red, or we get a red and a blue, or a blue and a red, or a blue and a blue. Okay. And we're going to assume that each of these outcomes is equally likely, which seems reasonable. Okay. Now we're going to define the random variable x to equal the number of red cubes in the sample. So here an outcome is a collection of cubes. The random variable is we're going to take that those cubes and return the number of red cubes in the sample. Now, to illustrate what that means, let's look at x as a function. X is going to take an outcome and return a real number. So, for instance, one outcome is RR. If we plug that into our function x, we're going to get the real number 2. Right? Because there's 2 red cubes in that outcome. Okay? Another outcome is red-blue. If we plug that into our function x, we get the output 1. X of blue-red is 1, again because there's 1 red cube. And then lastly, x of blue-blue is 0. Okay? So this random variable x can take on 3 different values, 0, 1, or 2. Okay? Now, let's look at calculating a few values of the associated probability mass function. So little f of 0 is, by definition, the probability that capital X equals 0. Well, capital X can equal 0 only when we get the outcome blue-blue. What's the probability of blue-blue? Well, there were 4 outcomes in our sample space, and exactly one of them did we have a blue-blue, and so the probability is 1/4. So f of 0 equals 1/4. Another value of x is 2, so to calculate little f of 2, that is, by definition, the probability that x equals 2. X equals 2 only with the outcome of red-red. Probability of red-red is also 1/4, because there's only one outcome in which we get a red-red, and 4 possibilities, so 1/4. Now, the last value of f is a little more complicated to calculate. F of 1. That is, again, by definition, the probability that x equals 1. X can equal 1 when we get the outcome red-blue or blue-red. The probability of each one of those is 1/4, so 1/4 plus 1/4 is 1/2. Okay? So there we have the different values of our probability mass function. Okay? Now let's describe the distribution in the 3 different forms. So again, the distribution is just a description of these different values of the PMF. Here we have the distribution in the form of a table. Across the top row, we've got the values of the random variable 0, 1, and 2. Across the bottom row, we have the associated values of little f, 1/4, 1/2, and 1/4. Okay? Now, sometimes we like to draw a picture of that, and we do that with what we call a probability histogram. So across the horizontal axis, we have the different values of x, 0, 1, and 2. The vertical axis, we have the values of f of x, and we have 1 bar for each value. The height equals the value of f of x. And so there we go. This histogram tells us the same thing as the table, just in a different form. Now lastly, we can find a formula. And here's a formula. F of x is equal to this. And so if we plug in 0, we're going to get out the number 1/4. If we plug in 1, we're going to get out 1/2, so on and so forth. Okay? Now, exactly how we found this formula isn't terribly important. What's only important is that it works. If we plug in 0, we get out 1/4. We plug in 1, we get out 1/2. We plug in 2, we get out 1/4. So those are 3 different ways of describing the distribution of this particular random variable. Now, whenever we describe a probability mass function, we should make sure that it satisfies the properties of a probability mass function. So let's make 3 observations here. Number 1, note that all the values of this PMF are positive. So that means it satisfies the first property of a PMF. Second, if we add up the values of f over the range of x, this right here denotes that we're going to add up the values over the range in x. So that's by definition f of 0, f of 1, f of 2. If we add those up, we get exactly 1. So that means this function satisfies the second definition of the second property of the definition of a PMF. Now, the third property isn't really something that we need to verify. It's really a description of how we use the probability mass function. Okay? So to illustrate that, let's suppose I want to find the probability of getting 1 or 2 red cubes in this random experiment. So in terms of the value of the random variable, it's the probability that x equals 1 or x equals 2. Another way of describing it is the probability that x is in the set 1, 2. So by the third property of the PMF, We calculate this by adding f of 1 plus f of 2, and we get those numbers from our distribution, 1/2 plus 1/4, which is equal to 3/4. So there's a 75% chance that I'm going to get exactly 1 or exactly 2 red cubes. Now, there was a definition, the generic definition of a probability mass function and a random variable. In this next definition, we're going to define a specific type of random variable that has a specific type of distribution. It says let x be a discrete random variable with k elements in its range. So k is some positive whole number. So we could have 5 elements, 12 elements, 15 elements. X has a uniform distribution, or is said to be uniformly distributed, if its probability mass function is 1 over k for each x in R. So what's important here is that k is some whole number, so 1 over k is a constant number. So we're saying here it's uniformly distributed if its PMF is constant. Think about what the word uniform means. It means like everything's the same. And that's really what we're saying here. The probabilities of all these different values are the same. And so to illustrate this, let's look at this simple example. Consider the random experiment of rolling a fair 6-sided die. So we're going to roll it once. So our sample space is 1, 2, 3, 4, 5, 6. So we have 6 elements in our range, or in our sample space. Okay. Now let's let the random variable x denote the number of dots that land on the side that lands up. So in other words, x is just really another name for our outcome. Okay. Now the probability, now all of these outcomes are equally likely. So the probability that x equals 1 is 1/6. Probability that x equals 2 is 1/6. The probability x equals 3 is 1/6, so on and so forth. So our PMF is 1 over 6 for each x in our range. So in other words, x has a uniform distribution. Okay. So a uniform distribution is rather simple because everything is equally likely. There's only one value to our probability mass function. Now, our next definition, we're going to define something similar to the PMF, but we're going to call it the cumulative distribution function, abbreviated CDF, is defined to be this. We call it capital F instead of lowercase f. Our input we're going to call b rather than x. And it's by definition the probability that x is less than or equal to b. So it's not the probability that x equals b, it's the probability that x is less than or equal to b. So now by the third property of our probability mass function, we can calculate that probability by simply adding up values of our probability mass function over all values of x less than or equal to b. Okay. So to illustrate this, let's look at this example. And this is really an example that we've seen before back in Chapter 1. Consider the random experiment of rolling 2 fair 6-sided dice and calculating their sum. Let the random variable x denote this sum. Okay? So down here in the corner, we have all of our possible outcomes. Here's our outcome from the first die, the second die, and then here's their sum. And so these values here are the values of our random variable. We see they take values between 2 and 12. And here in this table we describe the distribution. X goes from 2 to 12. There's only one outcome in which the sum is 2, so this probability here is 1/6. The probability that x equals 3 is going to be 2/36 because there's two outcomes there that equal 2, so on and so forth. Okay. Now let's calculate the value of capital F of 4. Capital F of 4 is by definition the probability that x is less than or equal to 4. Okay? Less than or equal to 4. So x is less than or equal to 4 means that x equals 4 or 3 or 2. So by the third property of our PMF, we calculate this by adding up f of 2, f of 3, f of 4. And so we just add up these three numbers right here. and we get 1/6, and we're all done. Now lastly, we're going to define two numbers that we call the mode and the median. Okay? The mode of a discrete random variable x is the value of f is the value of x at which the probability mass function is maximized. Okay? The median of x is the smallest number m such that these two probabilities are true. So the mode you can think of as kind of like the most likely value of x. F is a measure of how likely the different values of x are. We want to maximize that, and so that's the mode. The median is, you kind of almost think of it as like the number right in the middle. It's not really the number in the middle, but that's kind of a way to think about it. So we need a number such that the probability that x is less than or equal to that number to be at least 0.5, and the probability that x is greater than or equal to that number to also be 0.5. Okay. So let's go back to this example 221, which is the first example from this section. And that random variable had the distribution given in the form, in table form here, and graph form over here. Now the mode is equal to 1. That's the value at which the PMF is maximized. So that's the highest point here. So that's all there is to finding the mode. You look for the high point on the graph, and you're all done. Now, the median is equal to 1, and we know that that's true because if we calculate the probability x is less than or equal to 1, so that's x equals 1 plus x equals 2, 1/4 plus 1/2 is 3/4. That's bigger than a half. And the probability that x is greater than or equal to 1 is the probability x equals 1 plus the probability that equals 2, and that's also equal to 3/4. So because both of these probabilities here are greater than a half, that means that our median is equal to 1. And furthermore, 1 is the only value of x for which these two probabilities are at least 1/2. So that's why our median is equal to 1.